so to speak, the overarching theme of this series of lectures I'm going to give is, they're on Koncevich's work on the formality conjecture, and therefore the deduction of the existence of deformation quantization of Poisson manifolds. But there's a big story there. What I'm going to discuss is basically some of the ideas which go into the proof of those things. And I try to use the ideas so they link up with the future directions of this whole thing, which has got something to do with Grothendieck-Teichmüller groups, multiple zeta values and things of that kind. But sometimes those links will be not completely obvious. But now, if you sit down and analyze the proof of Koncevich's formality theorem, the proof I'm going to follow really is that due to Tamakin. So if you sit down and analyze that proof, you see it's a bit like sort of modern high-quality fusion cooking. What you do is you take some extremely exotic ingredients, rare exotic ingredients, swoosh them into a wok, slosh them around for a few days, and out comes the perfect meal. So what are the plugins? What are the exotic ingredients? The first, there are really three of them. The first is the theory of operads. And Bruno's covered that with great enthusiasm and style, I must say, over the last 3 weeks. So I will not say so much about that plugin, but I will plug in any bits I take freely from what Bruno has told us. The second plugin is the Deligne conjecture, and that's what I'm going to spend today on. The third plugin, which is the most exotic ingredient of all, in my opinion, is the plugin from the Etinghoff-Kazan quantization of Lie bialgebras. But actually, again, when you analyze what's going on in that plugin, the plugin is exactly just another proof of the Deligne conjecture. Right. So then you have to assemble so that's that plugin, that Etinghoff-Kazan quantization of Lie bialgebra would be the third. I'll spend the third day on that. And in the middle, there's the recipe for putting all these things together, and that's what I'll concentrate on in the second day of these things. Okay, so let me start at the beginning. I'm not going to assume anyone went to my lecture in the introductory conference, and anyway, that's so far away, you've probably all forgotten it anyway. So I'm going to start at the beginning. I'm going to start with the theory of Gersten-Haber algebras. In many ways, the theme of today is what is a Gersten-Haber algebra up to homotopy and what's it good for. But let me just tell you what a Gersten-Haber algebra is. So a GN algebra so that's G stands for Gersten-Haber, and there's an N there because there's an operation of degree N. Is a vector space, graded vector space, sorry. With two operations. The first operation, 1, is a degree 0 product so this is an operation from Vn tensor Vm into Vn plus m, degree 0 product, and this thing has to be a graded commutative. So that's the first operation. The second one is a degree n. Well, I call it product. It's Vp tensor Vq into Vp plus Q plus n. And I'm allowing myself the generality of having operations with shift degree by n because you see that they do actually occur. So, which is, let's see. I want to get some signs right, such that This is usually called the bracket. The bracket of AB is equal to minus 1 to the degree of A minus n, degree of B minus n, BA. Right, so this thing is that's its symmetry property. So now, then these things must satisfy certain relations, and the way I like to write the relations is like this. What so for the relations, introduce the operator LA, where LA of x is the bracket of A with x. Now you see, this operator, LA, is an operator of degree of A plus n. It raises degree by A plus n. And the relations are these that I want. This is 1, 2, 3. LA is a graded derivation of degree A plus n of the bracket. So that means when I swap this LA past anything, I have to introduce a sign minus 1 to the degree A plus n. The fourth relation, so that's this is a graded Jacobi identity. And the second relation is LA is a graded derivation of degree A plus n of the product. Okay, so this is a graded version of the Poisson identity. Okay, so that's what a Gerstenhaber algebra is. It's got two products, a graded commutative degree 0 product, this strange bracket of degree n, which satisfies the symmetry condition of a Lie bracket of degree n. And this operator is a derivation of both the bracket and the product. And that's how the two structures are intertwined.
The first product is associative.
Pardon?
The first product is associative.
Associative graded commutative. Associative graded commutative. Yeah. Yeah. Now,
most elegant way of formulating Poisson algebra in this grading
sorry?
situation. Introducing LA is a nice description.
It's the only way I can remember it.
You're the one.
Right. Now, the whole point, okay, so now what I want to study now, what I want to concentrate now on is examples. And the first example is our friend, the Hochschild complex. So let's think about the Hochschild complex. So, well, now this thing, so I'll start off, well, first I'll start off with any vector space. And then I'll write Cn of V to be Hom over the scalars, of course, V tensor n, linear homomorphism from V tensor n into V. So multilinear operations on n variables. Now, this thing has some structure. We've seen the structure I want to talk about, or some of the structure I want to talk about. And one way of saying it is these spaces, Cn, form an operad. But in particular, it's got these various substitution relations. The first one is circle I. Right? So this operation gives me an F in Cn dV, a G in Cm of dV, and gives me F circle I, which would be in Cn plus m minus 1 dV. And this is, I'll write it without putting elements, and therefore I think I'm suspended from having to talk about the signs. But the formula is this: it's F composed 1 tensor I minus 1 times tensor G tensor 1 tensor, well, however many times I've got left over. Right. What is it? Well, I'm not sure. I can't do such calculations at the blackboard. Right, but you slot G in the ith place. Now, of course, here it's F composed of that. Here, of course, if you evaluate this on a collection of elements, you'll introduce a whole pile of signs because you're moving some things past other things. Right? And I think the signs, the correct signs are precisely those signs. Right? I will stop after a while being careful about signs. I'm embarrassed to tell you this, but I think for most of the talk, I'll work over the rationals mod 2.
Was that exponent?
Pardon?
Where in the
How many slots have I got left? N minus I minus 1, isn't it?
Minus I.
N minus I, sorry.
Oh yeah.
Yeah. It's the only thing it can be.
Yeah. You have to add factor together.
Yeah. So there's that operation, and then there's the circle operation, which is sum. And here is I'm not. Again, I think the signs are exactly the right. I think when I write it like that, sum over I at circle ig. Right? I think that having done it like this, the signs work out correct. You get an awful mess of signs when you actually evaluate this on an element, but I don't need any signs at that point. Now, where am I?
The trick is that you incorporate the sign into the definition of tensor product.
Exactly, tensor product and the composition of tensor product too. F tensor G compose H tensor K. Well, there's a sign. So really, to get the signs right, you have to rigorously and unflinchingly apply the sign rules of graded algebra. For example, if you desuspend something, if you shift its degree and take d of it, you have to make a sign, right? So,
Or work mod 2.
Pardon?
Or work mod 2.
Over the rationals. Actually, these signs can be absolutely paralyzing, by the way. They really can. If you try to write them down, they will. After a while, it induces complete brain freeze. You just cannot think about anything at all about these signs. They're very destructive, these signs, I can tell you that. Anyway, sorry, that was a sort of heartfelt complaint on my part. You could tell I've tussled with these damn things. Okay, so now one thing I want to say about this is, well, suppose this is an important observation, I call it a lemma for want of something. Suppose I start with mu in C2 of VV, mu from V tensor is associative. It's a product, it's an associative product, if and only if mu circle mu is 0. I find that's a neat way of expressing the associative law. So in other words, the number of, and this will be a recurring theme, the number of associative products on V, on this vector space V, is exactly the same as the number of solutions of this equation. Right.
This lemma probably shows that in the formula for circle, you need the sign -1 to the power I minus 1 or something, because otherwise it's not associative.
Oh, you have to shift V here.
See what I mean? I think you're right.
It's all well.
-1 to the I.
-1 to the I. Right. So I've got those.
I need that homework. Like all the sign that's work.
Yeah, right. But I'm not going to say that because I'm supposed to give an exercise class at 4 o'clock, and if I do, then I'll have to do those signs in public. So that's the first thing. Now take A, V to be an algebra with product mu. Now I look at this. Now I look at the same setup, but with an algebra with a product in it. And I want to now think about what extra structure this induces. Well, the first thing it induces, rather obviously, is a cup product. And the formula for this is F tensor G maps to mu compose F tensor G. Right. So F tensor G, F
tensor G on the left. You said F tensor.
Thank you. Sorry. Okay. So that's just say take F of the first P variables, G of the next Q variables, and multiply them. So this product is associative. Not graded commutative. Now, the next thing it does for us is it gives us a differential. Define d mu, which will go from Cp of AA into Cp plus 1 of AA, and d mu is defined to be d mu of f is the, did I say the bracket? Sorry, I should have put the bracket here as well. On this board I should have put the bracket. I've introduced this circle operation, and there's the bracket operation, which is the bracket which is defined by the bracket of f and g is f circle g, and I have to get the right sign there, but I have to get a correct sign. I think the sign is minus 1 to the degree of f minus 1, minus 1 to the degree g minus 1. But there's a sign to be thought about there. So d mu of f is just the bracket of mu f, bracket of mu with f. And it's a consequence of the fact that mu, circle mu, is 0. It's a consequence of that fact that this thing actually is a differential. Actually, it's good exercise is to unpack this, right? You maybe have seen the Hochschild, the normal Hochschild differential in the Hochschild complex B, involving B of f evaluated on a list of a's. Is you pull what the a out on one side, multiply the a's inside, and pull the last one out on the other side. And it's a nice exercise in translating this formalism. In fact, d mu is the usual Hochschild co-boundary operator. And therefore, so I sometimes write d mu is equal to b, because that's the standard convention for the normal Hochschild boundary operator. Okay? So it's not difficult to check. Well, okay. Now the Hochschild cohomology of A with coefficients in A That's the definition. That's the definition of the Hochschild cohomology. Okay. Let's see. I just want to get my. Now, the next bit of structure. So we've got the circle I, the circle, the bracket, and the boundary. That's the data I've introduced so far. The next piece of data I want to introduce is the so-called braces. And the braces come about because, after all, I mean, I can slot a G in there. I can slot a G in at certain points. But if I've got a G and an H, I can slot them in at different points. Right? Or if I've got a G and H and a K, I can slot them in. First put a G, then put some ones, then a G, then some ones, then an H, then some ones, and then a K. And I can sum over all ways of doing that. And let me just say what that is. So here we've got F, G1, GK, and these are in the Hochschild complex. And then I'm going to tell you what I mean by the braces operation. A braces operation, and this is again. I'll write it out. I'll try again in order to get the signs correct. You know, in order to make a sign-free formula, I take the sum over I of some indexing set, and I put F circle composed with. Sorry, sometimes circle is circle, and sometimes circle is composed with. I hope it's clear which I mean when I write something. Anyway, I put 1 tensor I1. Tensor G1, tensor 1, tensor I2, tensor G2, etc. And I'll end up with and the sum is to be taken over all ways of slotting those in. Okay, right? It's supposed to be taken over all ways of slotting those in. So, for example. If the degree of F is less than K, right? Suppose F doesn't even have K slots, then there's no way of slotting them in, right? So if degree F is less than K, then this thing is 0. If degree of F equals K, well, there's only one way of slotting them in. Then this is F composed G1 tensor GK. There's only one way of slotting them in. If degree of F is K plus 1, well, then this thing has to be F composed 1 tensor G1 I write down the terms. I won't write the signs. Etc. Okay, I could put a 1. I could put a 1 in precise. So there'll be K plus 1, or is it K terms there, and so on and so on and so on and so on. And now you come to what I call the famous formula.
Just get the sequence G when you choose GK, and you interspate values of 1 in the middle.
Yes, you interspace values of one in the middle, exactly the right number, so that you use up all the variables of F, given that K of the variables of F are going to be used up by G1 and GK. G1 and GK. So now we come to the famous formula.
Is there a way to remember the sign in the definition?
I don't think there are any signs.
That's why
There is a way. Yes.
there are these blocks.
Yes.
Sorry, did you answer? It's okay. I put you in charge of answering all questions about science.
Yes, I put him in charge. Yes.
I think that's the best thing I've done today, frankly.
And there's a famous paper by Deligne and about churn classes, where he pretends, he put no signs,
Yeah.
and at the end he gives a recipe to restore all the signs.
Yeah.
Well, I would not advise to do that.
Okay, so now I want to give you the famous, what I refer to as the famous formula, which relates, well, this famous formula tells me what F circle G circle H minus F circle G circle H is. This is not an associative operation. This is not an associative operation. So I'm going to tell you what the associator is, and the answer is, and again I looked up the signs here. It's F bracket GH plus minus 1 to the degree G, degree H, F HG. Okay. Now, I mean, there's some combinatorics to do to get this formula, but you see you're slotting things in different places, and the other terms in this expression occur in pairs with opposite signs and cancel. So there is what I regard as the famous formula. Now, an immediate consequence of this famous formula, I think I'll stick to the main roots, is this. It tells us that, in fact, the cup product is commutative up to chain homotopy. D mu of F circle G, and then I'm just going to put plus or minuses. Consequence of that formula is that, if you this circle operation, the way to think of the answer is this circle operation is a chain homotopy between the cup product one way round and the cup product the other way round. So we see then that. Sorry, is there a question?
You didn't define the cup.
It was defined before.
The regression was not the notation.
It's just the cup product is mu.
You did not introduce a notation.
Yeah.
I didn't do the notation. Sorry. I got your point. F cup G is F mu composed. Okay, that's the formula for the cup product. So you see, this is exactly what makes the cup product commutative. So consequence, the Hochschild cohomology has a graded commutative product. This formula tells me that if f and g are cocycles, then the boundary of this thing is the difference between f cap g and g cap f. So therefore, the product is graded commutative in cohomology. Well, H star. So the bracket operation. This I should have said that d mu is a derivation of bracket. So, hence, bracket gives an operation, descends to a bracket operation from HHP of A Okay, so again, it follows that this thing is a derivation of the product. And so the theorem, which is indeed due to Gerstenhaber,
Sorry, John. It's probably obvious to most people, but I don't understand why the second and third term on the left-hand side are boundaries, or let's say the combination is boundary. Why is the left-hand side a boundary? Why is it
it's only a boundary if f and g are co-cycles.
Okay.
Right, if f and
d mu of something, the second and I mean, you can definitely write it as d mu of something. It is a co-boundary. Ah, okay, sorry.
right, if
But
f,
d mu of f is 0.
It's
if d mu of f is 0 and d mu of g is 0,
Sorry.
then f, that difference is okay. So the theorem is that HH is a G minus 1 algebra. And of course I mean with that product, with that graded commutative product and that bracket. Okay, so the theorem tells us, and these are calculations. You either use the famous formula, or hand calculations to tell you that in fact these things satisfy the relations they're supposed to for a Gerstenhaber algebra. So HH star is G minus 1 algebra. Now, why do I care about this? Let's see if I can. So why do we care? Well, remember, I'm sorry to go back over the stuff I went through in the first week of the conference, but I think it's important. So why do we care? Well, I suppose the fact that more than one of us cares is somehow an assumption. Well, you remember the theory of formal deformations. Okay, so I'm just briefly recall this. So we've got A in algebra, associative algebra. And we want a star product. Is a K of T over the field K, right, over K. Is a K of T power series on one variable linear product. Sorry, bilinear. Right, it's going to be K of T bilinear associated product on the formal power series in A, such that A star B equals A times B mod T. Here A and B are in A. Okay, so I take their product in this formal power series sense, A and B, just think of them constant formal power series. That'll give me a great big power series of variables, and if I just cancel all the first term is the product of A and B. And that's what I mean by a formal deformation. A star product is a formal deformation. That's another name for the same thing. And of course, the theorem we want to prove is that every Poisson manifold has a formal deformation of its product, and we'll control the first order term. But what we're after is proving a theorem about the existence of formal deformations in a particular geometric situation. I'll come back to that at the appropriate time. So, how does this all fit with the formalism of Hochschild cohomology? Well, of course, you see, I can write so the star product is determined by something theta from A tensor A into A formal power series in T. Since it's since it's bilinear over K of T, then it's just simply determined by what it does on A tensor A. And what we do is we write theta of AB is, well, it's the product, which I write mu of AB. Now, I interchange between writing products as just juxtaposition and putting a mu in front of them, plus C of AB, where C of AB is in A of T, and C of AB equals 0 mod T. Now, this product has got to be associative, but remember my little remark right at the first thing. Associative is the same as checking, well, that the if and only if theta circle theta equals 0, and since I'm not, which is the same as theta, the bracket of theta with 0, check the signs. So substitute this in, so I want the bracket of mu with
Same characteristic.
except in characteristic 2, which is the only case I'm honestly talking about.
Well, take the rational modulo.
So I have to write out this thing, mu plus c bracketed with mu plus c. And you see this is equal to mu mu plus mu c this term is 0 because mu is associative. This term, these two terms are the same because this has degree 2, this has degree 2. When I look at the sign, the sign becomes a plus sign in the symmetry. So this is equal to 2 mu c, right? You have to check on the signs there, plus cc. Okay, so associative if and only if, well, that bracket is 0, which tells me that d mu of c, because that term plus 1/2 c bracketed with c equals 0. So it's associative if and only if it satisfies, this is the Morikawa equation. So looking for star products is the same as looking for solutions of the Morikawa equation. Notice also that this Morikawa equation only uses the bracket operation. Okay? So it makes sense in any differential graded Lie algebra. Okay? So that's why we care. We care about this Hochschild complex because we want to find solutions of the Morikawa equation. Okay. So far, so good. Where am I? Okay, now next thing I want to do then is to tell you another source of examples of Gerstenhaber algebras. So I've explained the Hochschild complex, the Hochschild cohomology is a Gerstenhaber algebra, and we care deeply about that because of its relation with the star products. But now what I want to do is introduce d-fold loop spaces. And I want to explain how those give you another class of examples of Gerstenhaber algebras. So by this I mean I start with some topological space Y, and I look at the d-fold loop space of Y, by which I mean the space of all maps from a closed D disk relative to its which map the boundary, which map to y relative to a base point. Right, so my topological space has got a base point, and I look at the set of all maps from a closed D disk, which send the boundary to the base point. Of course, if D is 1, then I've got the usual definition of the space of loops. In fact, this is the same as the loops on omega D minus 1 of y. A little manipulation with these topological spaces tells you that the loop space of the loop space is the twofold loop space. Yeah, maybe, but allow me. Now, let me concentrate on the case D equals 2, because it's slightly, the structure is the same, but it's slightly more. Just needs a few more words. So concentrate on D equals 2. So we're looking at spaces X, which is loops 2 on Y. Now, one thing about a double loop space, so, well, of course, it's a loop space. There's a multiplication map, mu, from X cross X into X. The usual loop multiplication. Right? You take one, think of it as the loops on Y, and you do the loop structure with respect to the first one. But it's got another loop structure. Right? Well, I could have done it the other way around. I could have taken the multiplication, loops on Y cross loops on Y to loops on Y, and looped that. That would give me a different multiplication. It's got two multiplications. One.
I didn't understand the second one.
Pardon?
I didn't understand the second multiplication.
So the first multiplication was use the multiplication in loops on Y. The second was use loops on the multiplication in loops on Y. Right? There's a multiplication map from loops on Y cross loops on Y to loops on Y. Loop that, right? But I mean,
if you write it as maps from the cube, you can add in the first variable or in the second.
yeah, but now all I'm doing is now loop that thing. And that'll give me a map from loops 2 on Y cross loops 2 on Y into loops 2 on Y. Loops 2 on it, right? That's all I'm doing. Yeah, but I mean, you could do it in terms of cubical things as well. But
Cube, this side, this.
yes, that's exactly. But anyway, the point is, it's got two multiplications, and each is a homomorphism of the other with respect to the other. Therefore, by the Ekman-Hilton trick, the two multiplications are equal, and both are commutative. So the point is about this thing. This is homotopy commutative. Now, look at that formula over there. That says the cup product. Look at the formula at the top of that board there. That says a product is homotopy commutative, but in a different sense. It says the cup product is homotopy commutative in the sense of differential graded things, in the sense of chain complexes. And here we've got another product. It's homotopy commutative. So what I'm going to do is turn this into a commutative product using the fact that okay, sorry, let me. So now define operations on the singular chains of X. Okay, this means so the first one is the Pontryagin product. And this is just given like this: SPX tensor SQX, SP plus Q X cross X. This is the external product, the usual external product in homology. And now take the multiplication. Okay. So this is the Pontryagin product on chains, and it's not difficult to check. It descends to homology. In fact, Of course, it descends to homology. I just write down the same formula, but with SP and SQ replaced by HP and HQ. There's no problem with that. So it's got a commutative product. Now, next thing we do is choose a homotopy. In fact, there is a canonical one because of what you say. There's a canonical one, if you think of it in the right way, which choose a homotopy. Such that, well, f of 0 xy is mu of xy, and f of 1 xy by the little discussion there exists such a homotopy, so you choose one. That gives you a chain level operation. What is this chain level operation? What I do is I go from S1 of the interval. There's a standard one chain there. The interval is itself a one chain. Tensor SP of x, tensor SQ of x, into SP plus Q plus 1 of I cross x, and then I apply the homotopy. This first one is just standard products, standard external products, and then I apply the homotopy. Now, what's the formula for this? Let me call. Let's call this operation lambda. And you find that the formula for the boundary of lambda is this. The boundary of lambda applied to AB plus, and there are signs, of course, lambda applied to boundary of AB plus, well, plus or minus. And here, star is the Pontryagin product.
So sorry, what's the link between lambda and what is the last but one line?
Beg your pardon?
The link between lambda and the last but one line?
This one?
No, yes.
This is the definition of lambda.
So then we miss something in lambda, no?
Pardon?
There's not S1 of I.
Well, but there is a unit, a special element in the.
Yeah. So, I beg your pardon. I'm sorry, I've got your point. What I do is I take the identity map of this thing and regard that as a singular chain. Right? The singular chain is a map from the interval, so there's a canonical singular chain there. Then that canonical chain there, I take A and B. That gives me a chain of degree P plus Q plus 1. Right? So what I do is I apply this to, I call it iota tensor A, tensor B. And that will give me the thing which I call iota cross A cross B, the external product. And then I apply F star to that. And that's the definition of lambda AB. Okay, you're right. Thank you. Now, I'm afraid I erased the formula before, but this is exactly the same formula as the formula for the cut product. As the formula for the cut product in Hochschild cohomology. It's exactly the same formula, apart from the fact that this operation raises degree by 1. So you can guess what I'm going to say. this shows the Pontryagin product is commutative in homology. To and again the right signs. Right. Gives a bracket in homology. This thing is called the Browder operation, by the way. And the whole shooting match in homology gives you a Gerstenhopper algebra. A G1 or G plus 1 algebra. So what I've done is I've converted the product in the double loop space into a product in homology. The fact that that product at the space level is homotopy commutative into a fact that the Pontryagin product, that is this corresponding product in homology, is commutative, and you get an operation, the Browder operation. And then there are some formulas you've got to check, but this is another example of a Gerstenhopper algebra.
I'm a bit confused. I mean, in some sense, you didn't use that you had a double loop space. You just used that you had a product which
is homotopy commutative.
But I guess that you need also to ask its homotopy associative in some sense to get your D algebra, right?
Oh, you're absolutely correct. Yes, you're absolutely correct. You're absolutely correct. I'm being very, very glib about associativity. Yes, of course. You have to check that the product is associative. Right.
But you don't need a double loop space.
No.
No.
Space of an H space. Loop space of an
H
H
space
space.
with a homotopy commutative.
Yeah. Loop space of an H space. Exactly. Yeah.
Oh, we suitable garçon.
Yeah. Okay.
I wanted to make exactly the same.
Okay. Thank you. Now, sorry. Okay. Now, just to tell you, there's some force in this. There's some sense in this. This is good. Let me tell you a theorem of Fred Cohen's. This is due to Fred Cohen. The homology of the double loops on the double suspension of X, okay? The homology of the double loops on the double suspension of X is the free G1 algebra. I should have put rational coefficients. Much of what I've been doing hasn't used rational coefficients, but here I'm certainly using rational coefficients. Generated by the homology of X. Okay, so that's a complete computation of the rational homology of a double loop space. I've packaged in a very nice way. It's the free Gerstenhopper algebra generated by the homology of X. But actually, by the way, so side remark. Omega 2 of the double suspension of X is the free is actually the free double loop space generated by the suspension of X. There's a map. So remember in all this, I'm using a certain adjunction, which is that the maps from A into loops 2 on B is the same as the maps from the double suspension of A into B. Okay? Allow me that, and I'll show you why this is the free double loop space. You see, first of all, that tells me that there's a map from X into loops 2. It's adjoint. Over here, it corresponds to the identity map from X, from the double suspension of X to itself. Now I can double loop. Now I can take loops. Now I can apply loops on the suspension, double loops on the double suspension X into double loops on the double suspension of the double loops on X. Now there's a map there's a map which cancels these two out.
It's similar to sigma.
That should be 2 omega and 2 sigma.
Sorry, I beg your pardon. I've done completely the wrong thing. I want to show it's the free double loop space given by that, right?
Right,
So what I should do is give me another double loop space, right? Then I'm going to construct a map from. Give me another double loop space and a map from X into a double loop space, right? I'm going to prove it's free. Therefore I must construct a map from the double loops of the double suspension of X into a double loop map. Perhaps this is not. It was not wise to do this. Perhaps it's too. Well, anyway, I'm going to carry on. So I need to construct this. So what I do is I take my map X into omega 2 of X, omega 2 of Z, and I double loop and double suspend this map. Right? Apply that to it. Now, again, look at the adjunctions. You see there's a map from the double suspension of the double loop space of Z to Z. Right? So those two I can cancel out and get myself to the double loop space of Z. Well, maybe that remark is totally meaningless because I didn't explain it very well. But there is a sense.
It's just playing with that.
It's just playing with that adjointness. Just playing with that adjointness there, right? And so it's the point I'm trying to make is it's rather a neat result, which tells you that the homology of the free double loop space on X is the free Gerstenhaber algebra on the homology of X. That's the analogy I wanted to bring out. I perhaps haven't explained it as well as I should, but that was the point I wanted to bring out. Right. Where am I? So the Deligne conjecture. That's.
Would say one of the Deligne conjectures.
I told this story before. You look in Wikipedia. You type into Wikipedia the Deligne conjecture, and you come up with a long list of things. But so first, I'm not yet able to formulate it precisely. So this is vague version. And vague version is that this parallel between the structure of double loop spaces and Hochschild homology is not a coincidence. Right? So, in other words, the Hochschild complex should have the same algebraic structure, right? You see the parallel all along. There's a homotopic commutativity. That homotopic commutativity makes the product commutative and gives you a new operation. And that's really all that's going on there, right? Now, of course, I mean, this is a vague conjecture because I don't know what the structure of the Hochschild complex is. Right? I don't know what the structure of anything is. And this is precisely where operads plug in. This is precisely the point at which operads come in. What do I mean? What do I mean by the same algebraic structure as this? Well, it's going to be an algebra over some. It's going to be an algebra over some operad, like something related to little disks operad. And the Deligne conjecture is once I know this is an algebra over some operad, the Deligne conjecture would say this is an algebra over the same operad. Now, so that's the nature of the game. But now notice something funny is going on, right? Because there's a subtle change of signs here.
Plus 1 and minus.
Plus 1 and minus 1. Right? So don't expect life to be easy. Right? There's some kind of duality going on, or something like that. Right? But remember that the Hochschild complex is Hochschild homology is a G minus 1 algebra. The bracket is degree minus 1. Whereas the homology of the loop space is a G plus 1 algebra. The bracket is degree plus 1. So there's some change of signs which is going to introduce, of course, as it always does, a major headache. Okay, so I have to formulate this now. So I have to introduce the little disks operand. So the space I'm going to be interested in D, N, K. So this is the space of K linearly embedded N disks in Dn, the unit disk. Oops. So the pictures, which I'm sure you've all seen, are things like this. Well, it's not linear. So ways of placing a disk in a disk, right? Ways of placing. That's that's a little 3 disks. So you see that these disks are parameterized by 2. Each disk is parameterized, ordered. So these come like this: 1, 2, 3. Right? They're ordered. I need to have them ordered. So you see, this disk is parameterized by 2 things: its center and its radius. That's a point in Rn and an integer. This disk is parameterized by its center and its radius. This disk is parameterized by its center and radius. There's a map, therefore. And I'm sorry about the notation, but that's the way it goes, I'm afraid. This space is the space of K ordered distinct points. Ck of Rn is the configuration space of points in Rn. And there's such a map. To this collection of Kn disks inside the disk, I assign the centers. The fibers of that map are contractible, right, because of the choices of radii, which satisfy certain conditions. So this thing is a homotopy equivalence. Okay. So this thing, all I've done really is replaced Rn by a disk, and replace the points by the distinct points in Rn. I've taken them up to big disks inside Rn.
You enlarge the risk. You enlarge the vessel and you reduce.
Yeah, exactly. Yeah. as you say, enlarge the container and reduce the tubes in the container. Now, these spaces are let me just say something then about the topology of these spaces. Right? So, if let's see, pi 1 of dnk is trivial. They're ordered.
Did you say that the disk have disjoint interior?
I didn't, but I meant to. I certainly should have. The disks have disjoint interiors. That's the condition I must have on them. I don't want them overlapping anywhere. But
For the physicist, it means that as soon as the dimension of a spacetime is 3, there is no parastatistics. You have only boson invariance.
I'm very happy. I'm very happy to know this.
No, it's important.
No, I understand. Yeah.
When you have a physics in a medium which is two-dimensional, then of course
Yes.
you cannot. The statistics is much more complicated than the statistic which is usually Fermion or boson, which is commutative or anti-commutative.
Right.
It's much more. And that's exactly why.
Okay, so if n is 2, pi 1 of dnk is pi 1 of ck of Rn, which is the pure braid group on k strings. Right? And you should the way you should picture that, of course, is just think of a loop in the configuration space and draw it as a path which goes from the configuration space of these points up here to these points down here with the same set of points but shifted. And think of that path, and you see it makes a braid. A braid, but the braid has the property that the first string reconnects back to the first string because it's a path in the configuration space of ordered points. Okay?
And by going to suitable covering, you should cover also the braid group itself, not only.
Yes, there's obviously an action of the symmetric group on either of these spaces. And if I quotient by that, if I take that action is free because they're distinct points. If I quotient by that, then it changes this fundamental group to the symmetric group and this fundamental group to the braid.
That's what I said. For physicists, as soon as dimension is at least 3, the symmetry is governed by the symmetry group. In dimension 2 is governed by the braid group. And it's quite different.
Yeah. It matters whether you go over or under.
Important.
Yeah. The second thing I want to say is that if n is 2, again n is 2, then pi j of either of these spaces so these spaces only have one homotopy group. They're k pi 1s, right? They're k. This space is k bk1. Okay, it's not difficult to prove that in fact that this space has higher homotopy groups, but I won't do it because I'm already running behind. The next thing I want to say is that actually we also know the cohomology of these spaces. Well, I'd say for its the configuration space because you see there are maps Pij from this configuration space of Rn into Sn minus 1 defined by Pij of x1 up to xk is xi minus xj divided by mod xi minus xj. The points, remember, are distinct. So that will give me a collection of maps from this configuration space to the n minus 1 sphere. So that gives me a bunch of cohomology classes. The sigma is the generator. It's a chosen generator. It's fixed once and for all. The chosen generator. So I can take those maps and pull back the fundamental class of Sn minus 1 to get myself a collection of cohomology classes. And then this famous calculation is the ring generated by the AIJs subject to the relations well, the first relation is AIJ is equal to minus 1 to the n AJI. And that is because, of course, the antipodal map of Sn minus 1 has degree minus 1 to the n. It involves n changes of sign. The second relation is the AIJ. This is the one I can never get right unless I... Sorry. AIJ AJK plus AJK AKI plus A is 0. And the second condition, the third condition I have to put in is that AIJ squared equals 0 if n is odd. N is odd, so n minus 1 is even, right? N minus 1 is even. So it's not the square is not automatically 0, but it's got to be 0 because the cohomology class comes from the cohomology of a sphere. Okay? Now I want to now make a connection of this thing with operads, and I'm going to connect it to the Lie algebra operad. So if you compute a bit with this, you'll find that the top dimensional cohomology is, I call it ln of k, which is hk minus 1. I think I mean hn minus hk. I don't know, sorry. I've got to write some combination so it's sensible in the case when k is 2, right? Because when k is 2, it's just an n minus 1 sphere, right? It's a homotopic to n minus 1 sphere. So when k is 2, I get n minus 1 here, right? At the top, okay? So I think I've now got the dimensions right. This thing, well, look, these points are ordered, therefore this thing carries an action of the symmetric group. So this is a representation of the symmetric group. Which one is it? Well, I'm not going to write down the Young tableau for it, what I want to do is connect it up with something Bruno said in his lectures. Remember, Bruno told us how if you know the free thing, right? If you start with an operad and you know the free thing over that operad, you can recover the operad as a subspace of the free thing. Okay, so I'm going to tell you what it is. So start with L, the free Lie algebra. I'm going to be completely confused by the order which so I'll stick to my notes. Right. L.
So, is it dimension n minus k minus 1 factorial?
Yes. Yes, k minus 1 factorial, yes. So you tell me. Right. So take this is the free graded Lie algebra. Generated by xi in degree by the xi okay, so that's just getting signs, right? Putting these to have a degree. That's it. Now take the linear part of this.
When you mean the algebra, you mean super the algebra or the algebra?
Pre-graded Lie algebra.
Okay.
So graded Lie algebra. So you put the signs, right? You put the signs, and the signs are determined by the degree of xi.
When people call it super.
Oh, sorry.
Not the same. Not the same.
But the bracket is of degree 0.
No, the bracket is degree n minus 1.
Okay.
Sorry, the bracket is degree 0. I beg your pardon. Sorry, yeah. Sorry, the bracket is degree 0, but the generators have degree n minus 1. Right, so you'll get some signs, right? But the signs won't involve anything to do with the bracket. They only involve the degree of indexes. So this thing is the linear part of this representation. By which I mean that part of this free Lie algebra, which only involves xi once and only once, right? So if you see every xi occurs once and only once in the formula. So it's things like k equals 3, right? Then it's things like x1, x2, x3 is allowed, and all permutations of that. But x1, x2, x1, not allowed. Okay, so you each in the bracket you write down, you see xi occurring once and only once, right?
There is some. So is it the same as graded, or because ln of k above? You say sits in degree n minus 1 times k minus 1, and what you constructed here sits in degree n minus 1 times k. There is some mismatch.
Oh, I'm sorry, I shouldn't have a k one.
I mean, if you put generators in degree 0 and say that the bracket is of degree n minus 1, this would has a better chance to.
I think there is a mismatch here.
You should desuspend by n minus 1 the result of that. You want a Lie algebra which somehow acts on the n minus 1 suspension of something. You see what I mean? You should.
This is the right dimension, right?
Yeah.
This is the right dimension because of the case when k is 2. Now, how many variables do I put in my Lie algebra? I certainly want.
No, because if you want to have an isomorphism between H and L, you
Yes.
have to desuspend L in the end by a desuspension of degree minus n minus 1, so 1 minus. So it is coherent. It is coherent.
But what about the number of variables I've got?
That's okay.
That's okay.
Sure.
Yeah, I think that's right. I think that's right. Yeah, I think that's right. That's right.
So yeah,
Yeah, but right. I mean, right? I could desuspend the x's and have a bracket of degree n, of course. Right. Which is what you just said.
Yes.
Okay, sorry. Okay, so well,
You said in linear part that all have to agree exactly once or at most once?
and most ones.
Exactly once.
Exactly.
The multilinear part.
Exactly.
Well, that's why I'm asking.
Exactly.
Sorry, I beg your pardon. Once and only once. Sorry, once and only once. Go back to this example. I mean x1, x2, x3, right? So it's the 3D bracket on 3 generators, right? It's a 3D bracket on 3 generators.
X1, X2 is not allowed also.
This one is not allowed, right?
No, but also something of degree different from total.
No. It's, everything must occur once and only once. Thank you.
Total degree K.
Yeah. Oh, sorry. Okay, and so the theorem is that, in fact, this is that representation. Now you know from what Bruno said that actually it follows, therefore, that this is the kth space in the Lie operad. Right? Exactly translating something Bruno said, it follows that this thing is the kth space in the Lie operad. Right? Actually, right. I'm not going to divert myself too much on that.
Up to suspension.
Up to some suspension. Yeah. Isomorphic to the kth space in the Lie operad.
Not as an SK module, but
as a graded vector space. Yes. Okay. Right. So so I've said something now about the cohomology of that, the cohomology of these configuration spaces, and related them to Lie algebras. In fact, this is a subtle point. It's related to Lie. So at this point, we're supposed to be friends, if you like, with these spaces. Now, the next thing is we actually get an operad structure. We actually get an operad. This is so. So this is going to be an operad in the category of spaces. Okay. So with Cartesian product, therefore. So what I have to give, in order to give the operad structure, I have to give the composition laws. And I'll just tell you what the composition law, so what I claim is the collection forms an operad in topological spaces. So I'd have to give certain composition laws, and these composition laws are disks in disks. So for example, I just write down one, dn2 cross dna cross dnb into so I start with a configuration of 2 disks like that, and here what have I got? A configuration of disks in a disk and another configuration. Oops. And what I do is I put the first one here, remember these are ordered, I put the first one in there, scale this down, put it in there. I scale this one down, put it in there, and then I erase the boundaries of those things. And then you see a configuration of 1, 2, 3, 4, 5, 6, 7 disks in a disk. Okay, so I'm not going to say any more about the composition law. Notice, by the way, that you can't do this if you choose points. You don't know how to insert a point in a collection of points in a point. You do know how to insert a collection of disks in a disk. Right? So this is a non-trivial step.
The board is a disk of infinitely small entities.
Yeah. Now, next thing I want to show you is that.
But you could have just used framed points.
Well, that would be the same. That would be. Yeah. Okay. There are lots of things.
Oh,
you
but
could
then
have
you
done.
don't specify the radius. I mean, you just specify a frame.
Yeah. Okay. I suppose. Yeah. But this is definitely. I mean, there are lots of different ways of making this basic construction, and that's important that there are different ways of doing it. But this is the way I'm going to do it. Okay. Now suppose you have. So the first point to make about this is that a double loop space is an algebra over this operad. Well, look, let me just. Why is that? Suppose I've got.
I think it's only true if n is equal to 2.
Yeah.
No, I'm going to put 2. I'm going to put 2 because that's all I'm going to do. That's what my drawings are. That's all I'm really going to use. But of course, the constructions are valid for n. So suppose I've got 2 disks in there, and I've got 2 maps, right? F from D2 into Y, G from D2 into Y. Then, of course, I can scale this D2 down there, down to this one, and apply F. I can scale this D2 down to that one, and apply G. Remember that this has to send the boundary to the base point, and the boundary to the base point. And outside these 2 disks, I map everything to the base point. Outside the interior of these 2 disks, I map everything to the base point. Right, so again, I'm not good. I mean, I hope that. I mean, it's a sufficiently intuitive construction that I hope that just makes sense. 2. If Z every double loop space, every C2 space is a double loop space up to homotopy. Okay, that's the way to say that. So in fact, to say something is a double loop space is exactly the same, homotopy theoretically, as saying it's a D2 space. One should really take care about this and go to Boardman and Vogt to get the fully correct statements, which is what Ike was doing.
2 has nothing special here.
2 has nothing special. Any connected is special, right? Connected is special, of course, right? But 2 is nothing special. Of course, you have to construct. The point is, you have to construct Y.
It's an n loop space.
Yes, a Dn space is an n-fold loop space. Now then, okay, so this long and involved story is a way of telling you what the algebraic structure on the Hochschild cochains should be. So now, so I've got this topological operad. From this, of course, I can construct a differential graded operad by taking the chains. Right? If I've got a topological operad, its chains becomes an operad in the calculated chain complexes. And from this, I can construct a graded operad now, remember, to give an operad, you have to give yourself a collection. So Dn, by Dn, I mean the collection of spaces Dn of k greater than 1. So by this I mean the collection of chain complexes and by this I mean the collection of graded vector spaces or abelian groups, whatever they might be. And because I started with the topological operad, each one of these inherits the corresponding, each one of these inherits the corresponding structure. So I think I'm going to say now what the conclusion are. I'm conscious that it's 12 o'clock. And break and maybe explain that a bit more next time. Right? So follows, just as a double loop space is a D2 space, that the chains on a double loop space is a chains on the double loop space of X is a chains on Dn algebra, right? Just because a double loop space is an algebra over the space operad, its chains would be an algebra over the chain operad, right? And now I can state the Deligne conjecture. The Hochschild cochains on AA is an algebra I finally come down to the Deligne conjecture. I've been playing this analogy. I've been trying to play this analogy between the structure of the Hochschild complex. So,
Put n equals to 2. And above 2. Yeah.
Oh, everywhere.
Yeah, everywhere.
Everywhere.
Well,
Wow.
Everywhere. This is. Oh no, I don't. No, I can leave n there. I can leave n there, but
n should be
okay. So you actually you come up with a precise. So I've tried to play what I've tried to do is play the analogy between the structure Hochschild cohomology has, the structure of the homology of a double loop space has. Actually, you see some remnant. You see this structure permeating at a slightly higher level in terms of commutativity, cup one, the bracket, and so on. But actually, the full statement is that, in fact, just as this is an algebra over this differential graded operad, the Deligne conjecture is that, in fact, this should be an algebra over the same operad. Okay. Okay. So I think I'll stop there. What I want to do is to, well, we'll see how things happen this afternoon. We'll see how things evolve this afternoon. But what I want to do is to actually explain a bit more about this Deligne conjecture. It's not satisfactory. Somehow or other, you can't solve this conjecture in the way it's formulated. Because if you take an algebra and a chain on the little disk, you have essentially no way of combining them, right? You've no way. You've no context in which to put the two together. So in a sense, this is. I'm actually going to call this Deligne conjecture Mark 1. In a sense, you've no hope of proving this conjecture in precisely the way it's formulated, right? So I'm going to have to play with it so I can get a conjecture you can actually get. I also want to say, I hope, something about a proof of this conjecture, the Deligne conjecture. So what I want to do is play with the Deligne conjecture. I won't tell you why I care. Play with the Deligne conjecture so you get something you can think about. And I want to actually try to explain the very combinatorial proof, or I'm not going to explain the whole of the combinatorial proof, but the key ideas which occur in the solution of the Deligne conjecture by McClure and Smith. It's a very combinatorial thing, and you see the nature of the game completely changes. You do silly calculations with purely set theoretic objects. Okay, so, but that I want to try and explain this afternoon, or at least the key ideas.
So A is an arbitrary algebra, just to be
yes,
clear.
Associative algebra. A is an associative algebra, and the statement is that, right, this is the statement, that this thing is an algebra over that opera. So
you don't include the unit.
I don't think I need a unit. I don't think I need a unit. I think logically I don't need a unit. Psychologically I do.
If you don't, what a unit in the algebra is needed if you want to have the degeneracy operator in the simplicial side.
It comes down to something.
Yes. If you just want the boundary, it's enough to have the multiplication. If you want to have the degeneracy operator.
Yeah. If you want to normalize, you need a unit or something like that.
But
Yeah.
you know that normalize. I mean, you can get rid of the degeneracy in simplicial algebra.
No, I mean, the one answer is also that what I explained last week is that you model the category of associative algebra by the operad as, and this is the theoretical deformation complex maps from the cochain of as to the homomorphism of A. And there's no unit there. You do not, from the very beginning, you do not encode the unit. This gives you a deformation complex which controls the deformations of just the associative map, not the unit.
And you studied with the Grothendieck algebra. Was it some tools that you will need later, or was it motivation for here? I mean, it seems like there's
Well, in the end, the way I'm going to formulate the Deligne conjecture is to say that, well, the homology of this is a Gerstenhaber algebra, right? Therefore, the correct version of the Deligne conjecture should be, the homology of this is a G algebra. So the correct version of the conjecture is that the chain should be a G infinity algebra, where G infinity is the canonical Koszul resolution, which Bruno explained to us. So that's the correct version. It's not the correct version, but that's a version you can actually try to study. Right?